Hello, 8th grade. It's good to be back. I hope you guys had a good and relaxing 2 weeks and a little bit. I'm sure we get to hear all about it, but for now, in this video, let's get back into the swing of things and focus on our lesson. I know it's been a long break, but I want to do a little recap of what we've done in lesson 4 and 5. In lesson 4, we talked about, and here's a little summary, we talked about how banks actually give us interest or charge interest. So we talked about simple interest and compound interest. And we know that simple interest is calculated once a year. So that becomes a linear graph, which will look something like this. So for simple interest, if I were to graph the amount of money that I would get in, it would be something like a line, like a linear graph. Okay, so starting from 0 and it goes up. The second one was the compound interest, which is calculated once per period, and then each period the interest becomes part of the principal, so the line will be an exponential growth, something like this. Okay, so there are two different ways of calculating the interest. So on lesson 5 we talked about also the power of the exponential growth, and we had this example 2. If you remember, we had these two functions and we were supposed to find out these f of n values. So once we graph it, we ended up with something like this. Like the blue line represents the linear function and the red one represents the exponential function. So these are the two changes that, or the two type of functions that we've seen so far. So now going back to lesson 6, we're going to talk about the exponential growth again, but we're comparing the linear and exponential models of the population growth. So if we read exercise 1, we see that we have two graphs, the world population and the US population, and the graphs look almost identical. If you look at them, they almost look like they're the same graphs. So let's read along exercise 1. Kelly and Joe examining the population data and the graphs below for a history report. Their comments are as follows. Kelly: it looks like the US population grew the same amount as the world population. But that can't be right, can it? And Joe says, well, I don't think they grew the same amount, but they sure grew at the same rate. Look at the slope. Now remember, that's what he says, look at the slopes, because the slope represents the rate of change. Or we can say how much they grew, the growth rate, or the growth rate. So let's look at the first question. Is Kelly's observation correct? Why and why? Well, if you actually pay attention to the scale that is on the vertical axis, we realize that this on the world's population increases by what? 1,000, 2,000 increases by 1,000. Or if you look at the world's population, we see that the graph on a y-axis increases by what? From 50 to 100 to 150, it increases by 50. So to answer question A, we can say no, the world population grew by a greater amount as shown by the scale. So Kelly is not right. The world population, which is this graph, grows by a far greater amount, because when we look at the y-axis, we realize that this goes by 1,000, whereas the US population grows by 50. Now let's look at question B. Is Joe observation correct? Well, Joe also ignored the scale of the two graphs. Okay, the rate of change, which is basically the growth rate or the slope, is much greater for the world population than the US population. Okay, so we need to make sure that we understand these vocab words. Rate of change is the same thing as growth rate or slope. Okay, so we can clearly see that from this point to this point, maybe this is 180 over here. So from what we grew from 150 to 180, 180 minus 150 is 30. So we grew by 30 million. Whereas from this point on the world population, let's say this is 2500, to this point we go from 3000 to, let's say, 2500. We grew by 500 million. There's quite a big difference between 30 and 50. So these are the rate of growth for both. We're going to answer question C together, and then I'll let you answer question D. Okay, question C says, use the world population graph to estimate the percent increase in the world population from 1950 to 2000. So this is the world population from 1950 to 2000. We're basically starting at 2,500, kind of like in the middle here, and we go all the way to 6,000. So basically what we had was in 1950 the population was 25,000 million, which is 2.5 billion, right? And in 2000, year 2000 was 6,000 million, which is 6 billion people. So the way we do that is we take 6,000, let me change the color, 6,000, which is the end population, minus 2,500, and then we divide by our initial population, which is 2,500. Okay, so once we compute that, we're gonna end up with 140%. Or that's 1.4, but since they 1% increase, we use that 140%. Okay? So for question D, we're going to use the same thing, but instead of doing it for the world population like we did in exercise C, we do it for US population. Okay, so find out what is the population in 1950 and the population in year 2000 for the US population, and then find the percent increase. So your correct answer should have been population in 1950 was 150 million, and then in 2000, year 2000, it was 280. So once we take the end population minus the initial population divided by the initial population, we end up with 87.87. Okay, this is point here, which ends up being 87%. So we notice the difference between 87% to 140% for the world population. It's quite a big difference. So the question E says, how does the percent increase of the world population, which I shorthand WP, compared to the US population, USP, over the same period of time? So from 1950 to 2000, we notice that the world population increases at a much faster average than the US population. Question F says, do the graphs above seem to indicate linear or exponential population growth? Now, by looking at the graphs, they look to be linear. And I just want to show you how to calculate the average rate. Okay, so you take in the first one we ended up at 6,000. So we subtract, and then initial was 2,500. So that's 300 or 3,500, and then we divide that 3,500 divided by how many years we have. So from 1950 to 2000, we have 50 years. So divide 15 to 3,500 and you end up with 70. Okay, so the world population increases at an average rate of 70 million per year. So the same thing we did for the US population. If you look at the graph, we ended up at 280, and the initial one was 150. We started at 150, so the difference is 130 divided by the amount of years we had, 50 years. We ended up with 2.6. So the US population increases at an average rate of 2.6 million per year. Okay, question G. Write the explicit formula for the sequence that models the world population growth from 1950 to 2000 based on the information in the graph. Assume the US the population in millions in 1950 was 2,500 and the year 2000 was 6,000. So this is very important because this question looks like it's going to show up very similar like this. It's just going to show up on the star. So how do we find the formula that models the population? So if I know that my initial population was 2,500, I start with 2,500, and I know I got to add something. Okay. So the growth rate, I'll have to look at the growth rate, and I realized from the previous question that the growth rate for the world population was 70. So I know that I need to add 70 and then times t. And t represents the number of years after 1950. So t equals number of years after 1950. Okay, so this is our f of t. Okay, so this will be our formula. So it's important to point out that this is a linear formula, which is, it's a linear graph. Now, if we look at the next exercise, we realize that we have a graph that does not look linear. So we're gonna answer these questions as we go along. So how is this graph different from the previous graph? If you look at the timeline over here, we realize that we're starting with 19 or 1700s, not from 1950 like the previous one, and we looks like from 1850 it looks like it takes an exponential growth. So question B, if you look at question B, does the behavior of the graph from 1950 over here, 1950 to 2000, so this portion, does it match what it shows in the exercise 1? So in question B, we realized that, yeah, both of these population are the same as in exercise 1, but question C says, does the graph from exercise 1 is somehow misleading? And yes, it is, because if you examine from a longer period of time, like from 1700s all the way to 2000, we realize that its population has grown exponentially. So in exercise D, they give us the formula for the exponential growth, which this number represents the beginning value, the original value, and then this represents the growth rate and t represents the number of years after 1950.